Hello everyone. In this lecture of the probability theory course, we'll be talking about functions of random variables. In many situations, we have a random variable defined in terms of another random variable or in terms of another set of random variables, and we might be interested in finding the probability distributions of the new random variables. That's what we call functions of random variables. So we will start in this lecture with a method called the inverse transformation approach, and we will use it to find the probability distributions of new random variables defined as functions of known discrete random variables. We will do the same for continuous random variables, and finally we will use another approach called the moment generating function approach to find the probability distributions of random variables defined as functions of known random variables. Let's start with the inverse transformation approach, and we will focus this discussion on discrete random variables. The rule says that if we have a new random variable y, which is defined as a function g of random variable x, if that function is a one-to-one function, which means for every value of x there is only one corresponding value of y, the new random variable, then the inverse function exists. That is, we can find x equals g inverse of y, or for every value of y there is only one corresponding value of x. If this is the case, then the probability mass function of the new random variable y can be obtained as fy at any value of the random variable y small has the same expression of the BMF of x, that is f sub x. However, the argument here is g inverse of y. Let's try to under this rule in an example. Let's assume that we have random variable x, and this random variable x has a BMF f of x equals, for example, 0.5 for x equals 1, 0.3 for x equal 3, and 0.2 for x equals 4. So this is a discrete random variable whose range is 1, 3, and 4, and the probability mass function corresponding to these values are 0.5, 0.3, and 0.2. Now let's define a random variable y which is equal, for example, 3x plus 2. Is that one-to-one relation? Yes, for every value of x there is only one value for y. So we can find an inverse relation. We can find x in terms of y. So that is x equals 1 over 3 y minus 2. So in order to get the BMF of y, fy at a certain value y is equal to the BMF of x at the corresponding value of x. So that is 1 over 3 y minus 2. So for example, if we want to get fy at for value y equals 0, so that is f of x 1 over 3 of y here is equal to 0, so that is minus 2. This is f of x of negative 2 over 3. Is this one of the values of x? No. So this probability is equal to 0. Similarly, we can get the BMF of y at any value of small y. However, it makes sense that we can expect that for these values of x, there are 3 corresponding values of y according to this relation. So at x equal to 1, this corresponds to y equals 3 plus 2 equals 5. And at x equals 3, the corresponding value is y equals 3 times 3 plus 2, that's 11. And for x equal 4, the corresponding value of y is 12 plus 2 equals 14. So we can say that the BMF of y is such that the probability that y equals 5 is 0.5, the probability that y equals 11 is 0.3, and the probability that y equals 14 is 0.2. 2. And for any other value of y, the BMF will be equal to 0. In order to make sure, let's, for example, substitute here or find the probability of y equals 14. So modifying this relation, that will be f of x of 1 over 3, 14 minus 2. 14 minus 2 equals 12 divided by 3, so that is f of x of 4. Fx of 4, that is 0.2. So the BMF of y at y equal 14 is equal to 0.2, which makes sense from what we said a while ago. So for the discrete random variables, it is very easy. The values of the BMF do not change. If we have BMF values of 0.5, 0.3, and 0.2, they will remain 0.5, 0.3, and 0.2. However, these will be the probabilities that y takes a specific value, and this value is obtained from this relation, which relates the new random variable y to the known random variable x. If we have two random variables and these two random variables are jointly distributed, then we usually describe the two random variables using the joint probability distribution. If we have two new random variables and they are defined in terms of the original random variables, so in order to get the joint probability mass function of the new random variables, we follow a similar rule. So it says here that if you have y1 given as a function of x1 and x2, where x1 and x2 are the known random variables for which we know their joint distribution, and y2 is the second new random variable defined in terms of x1 and x2 using the function g2. So if both functions g1 and g2 are one-to-one functions, then we can find the inverse function such that x1 is uniquely defined in terms of y1 and y2, x2 is defined uniquely in terms of y1 and y2, where h1 and h2 are the inverse functions. In this case, the joint BMF of y1 and y2 can be obtained as f of the joint distribution of x1 and x2. However, we replace x1 by the function h1 of y1 and y2, and we replace x2 by the function h2 of y1 and y2. Let's solve this example in order to see how this formula is applied. Let's assume that we have x1 and x2 are two independent Poisson random variables with parameters lambda 1 and lambda 2. Since we know that the two random variables are Poisson distributed, then f of x1 can be written as e power negative lambda 1 power x1 divided by x1 factorial. Similarly, fx2, the BMF of x2 is defined as e power negative lambda 2 power x2 divided by x2 factorial. And since they are independent, then the joint distribution f of x1 and x2, and let's write the subscript here, x1 and x2, is the product of the marginal BMFs. So that is f of x1 multiplied by f of x2. So we have the probability mass functions, the joint probability mass function of x1 and x2. Now we want to find the distribution of random variable y, which is equal to x1 plus x2. So here we have only a single random variable defined in terms of x1 and x2. When we study the moment generating function approach that we will study later, we will revisit this problem again and see how we can solve it using that approach. But for now, the rule that we can use is a rule that ties or relates two random variables to other two random variables. So in this example, since we have only y equals to x1 plus x2, then we can define arbitrarily another random variable. So let's start with assuming that we have y1 equals to x1 plus x2 as given, and let's define another random variable y2, and for example let's assume that it is equal to x2. In this case the relation is easy. The first step is to find x1 and x2 in terms of y1 and y2. So one of these two relations is straightforward, that is x2 equals y2. What about x1? x1 equals y1 minus x2. So that is y1 minus x2, and from the line below x2 is equal to y2, so we can define x1 as y1 minus y2 and x2 equals y2. It is also very important to define the range of x1 and the range of x2. So for example, we know that from the definition of the two random variables x1 and x2 that each one of them, since this is a Poisson random variable, so each one of them can take the values, the integer values from 0 to infinity. So x1 itself can take values 0, 1, 2 and so on, and x2 can take values 0, 1, 2 and so on. So for the two random variables, or for the two random variables y1 and y2, what will be the range of each one of them? For the random variable y1, since it is equal to x1 plus x2, then y1 can take values 0, 1, 2 and so on to infinity. For y2, here is the tricky part, y2 is equal to x2, so it can have values equal to 0, 1, 2 and so on. However, the maximum possible value of y2 cannot exceed y1, because y1 is equal to x1 plus x2, which is equivalent to y2 in this example. So y1 can be written as x1 plus y2. So the value of y2 cannot exceed the value of y1, because y1 is equal to x1, which is 0 or something positive, plus y2. So the maximum possible value of y2 at any given value of y1 is equal to y1. So y2 cannot grow indefinitely up to infinity unless y1 itself is infinity. So we have here the maximum possible value of y2 is equal to y1, while y1 itself can grow indefinitely up to infinity. So now we know the one-to-one relations between the new random variables and the original random variables. We know the range of the two new random variables. The next step is to apply the formula directly. So the formula says that the probability mass function of y1 and y2 at any values of y1 and y2 is given as the probability mass function of x1 and x2. However, we substitute for every x1 with its function of y1 and y2, and every x2 with its function of y1 and y2. So it is f of x1 and x2, where we substitute x1 by y1 minus y2, and we substitute x2 by y2. Since the formula that we obtained one step earlier was e power negative lambda 1 times lambda 1 power x1, now x1 is replaced by y1 minus y2, of course, negative x1 divided by x1 factorial, which is now y1 minus y2 factorial, times e power negative lambda 2 power negative x2, which is now negative y2, divided by y2 factorial. So this is the joint probability of y1 and y2, where y1 equals 0, 1, 2, 3, and so on till infinity, and y2 is equal to 0, 1, 2, and so on until y1. However, the requirement was to find the probability mass function of y, which we named y1. So in order to find the marginal probability of y1, we need to exactly find the summation of the joint probability mass function over all the possible values of y2. So f of y1 is equal to the summation of the joint distribution y1 and y2 over all the values of y2. That's why it was important to define exactly the range of y2, such that this summation is for y2 starting from 0 up to y1. Solving this summation, it will be a straightforward summation, and when you follow the steps, you can reach the conclusion that this will be equal to e power negative lambda 1 plus lambda 2 times lambda 1 plus lambda 2 power y1 divided by y1 factorial. Moving forward, for continuous random variables, we will use also the inverse transformation approach to find the probability density function of a random variable defined in terms of another random variable, or a couple of random variables defined in terms of other two random variables. Let's start with single random variables. So we have the same conditions that if we have y, a new random variable defined in terms of a known random variable as a function g, where g is a one-to-one function, then the inverse function exists. That is, we can express x as a function of y. Then the PDF of y can be obtained as the probability density function of x, but we substitute for each x with the corresponding inverse function of y. However, the added part here in the case of continuous random variables is that we multiply by this term, which we call the Jacobian. And the Jacobian is the derivative of x in terms with respect to y, or the derivative of g inverse of y with respect to y. This Jacobian exists here only in the case of the continuous random variable, because the function fy or f of x both represent probability density function. And in order to keep the area under the curve equals to 1, that is the total probability, this Jacobian is used to adjust, or is added to the expression of the new probability density function to adjust the area under the curve such that it totals up to 1. That was not used in the case of discrete random variables because, as I told you, in the case of discrete random variables, the BMF, the values of the BMF are not changed. The corresponding values of the values of y are the ones which change, but the values of the probability mass function themselves do not change. So the summation is still equal to 1, so there is no need for the Jacobian. However, as we will see in examples, the probability density function might change in values. However, we have to keep the total area under the curve equals to 1. That's why we have the Jacobian term. So you shouldn't forget the Jacobian term. Before we get an example, let's see another special case in which if y equals g of x is not a one-to-one relation. So for each value of y, there might be more than one value of x. For example, if we have y equals x squared, this is not a one-to-one relation because both positive and negative 3, for example, result in the same y, which is equal to 9. So if we know that y is equal to 9, what was the corresponding value of x? It might be plus 3 or negative 3. So that's not a one-to-one relation. However, if the interval over which x is defined can be partitioned into mutually disjoint intervals or k mutually disjoint sets, k non-overlapping intervals, such that within each of those intervals there is an inverse function such that x is defined uniquely by the value of y. So we have in the first interval x1 is equal to w1 of y, x2 in the second interval is equal to another inverse function w2 of y, and so on condition that each of those functions in each of those mutually exclusive intervals are one-to-one mapping. Then the PDF of the new random variable y can be obtained as summation over the k intervals for the PDF of x. However, we substitute for the value of x with the corresponding inverse function of w multiplied by the Jacobian, which is the derivative again with respect to the random variable y, and we perform the summation over all the k intervals. Let's start with this example in order to understand the previous formula. We have x, a random variable with normal distribution or Gaussian distribution defined as shown. And of course that means that the mean is mu and the standard deviation is sigma, or the variance is sigma squared. And we are required to find the distribution of y, which is equal to x minus mu squared over sigma squared. So one can first notice that x minus mu over sigma, for which x is a normal random variable with mean mu and variance sigma squared, this term defines the standard normal random variable. So that's a random variable with normal or Gaussian distribution whose mean is equal to 0 and variance is equal to 1. So we can, as a first step, mention that if we have a new random variable called z and this is equal to x minus mu over sigma, then we know from our previous knowledge that z will follow a normal distribution but the standard one, in which the mean is 0 and the variance is 1. That is the PDF of z, f of z as a function of z equals 1 over square root 2 by sigma squared here is equal to 1, e power negative 1 over 2 sigma squared, which is again 1, x minus mu, or z in this example, z minus mu, and mu is equal to 0, so that is z squared for z ranges from negative infinity to infinity. Next, we have y equals x minus mu squared over sigma squared, so that is z squared. So now we have a random variable, new random variable, y, defined in terms of random variable z, for which we know the probability density function. However, this relation is not one-to-one relation. For any positive and negative values of z, both correspond to the same value of y. However, we can split this relation between y and z into two intervals. One interval for z less than 0 and the other is for z larger than 0. In this case, if z is less than 0, then z will be equal to negative the square root of y, and if z is positive, then z equals positive square root of y. So we can write the relation between the probability density function of y and the probability density function of z as follows: Fy of y equals summation of Fz of the I, for example, times the Jacobian, where the Jacobian is the derivative with respect to y for the inverse function. Let's call it W I of y, sorry. So, and this summation is for I, which is equal to 1 to 2, because we have only two intervals, one interval for positive values of z and another interval for negative values of z. Of course, if we want to calculate the Jacobian for each of the intervals, so we can calculate them individually here. So for this relation, the derivative of negative square root y with respect to y, so that will be negative half y power negative half, and for this one the derivative will be similarly half y power negative half. However, notice that in the Jacobian we have to multiply by the absolute value of this derivative, so this negative sign will make no difference with us, and consequently once we complete the steps, we get the probability density function of y equals to 1 over square root 2 pi e power negative y over 2 times 1 over square root of y. Of course, this is 1 over 2 pi coming from here, and then e power negative half z squared. Now we have z is equal to, or z squared is equal to y, so we get e power negative y over 2, and multiplied by the Jacobian. For one interval it is half y power negative half, so that is 1 over 2 square root of y. The other term has the same value, and when we do the summation, the half is cancelled and we get this relation. Of course, we have to define the range of y. Since y is equal to z squared, then y is of course positive and it is larger than or equal to 0. For the case when we have two random variables, we follow the same approach. So we have y1 given as a function of x1 and x2. Similarly, y2 is given as a function of x1 and x2. And as we discussed for discrete random variables, the joint distribution of y1 and y2 is equal to the joint distribution of x1 and x2. However, we replace x1 by the corresponding function of y1 and y2, and we replace x2 with the corresponding function of y1 and y2. And in the case of continuous random variable, we have to multiply the whole PDF by the absolute of the Jacobian, where the Jacobian here is defined as the determinant. So this is the determinant of a matrix, and this matrix is defined as the first row is the derivative of x1 with respect to y1 and y2, and the second row is the derivative of x2 with respect to y1 and y2. Again, x1 and x2 are the original random variables, y1 and y2 are the newly defined random variables. Let's have an example to understand how we can apply this formula. We have random variable x1 and x2, and they are independent exponentially distributed random variables with parameters lambda 1 and lambda 2. So since they are exponential, so we know that the PDF of x1 is defined as fx1 of of x1 equals to lambda 1 e bar negative lambda 1 x1. Similarly, fx2 of x2 is defined as lambda 2 e bar negative lambda 2 x2 for both x1 and x2. Each of x1 and x2 is larger than or equal 0, because if we recall the exponential random variables, we had the random variable, the exponential random variable represents the inter-arrival times or inter-occurrence times, so it is positive random variable. Then we want to find the probability density function of a new random variable w defined as the minimum of x1 and x2. While we can follow the general approach in this problem, however, in this specific problem we can follow an alternative approach in which we try to use a simple method based on our understanding of the definition of the new random variable. The new random variable here is the minimum of two random variables. So this is sometimes called order statistics. Order statistics, in which we might be interested in finding the probability density function of the minimum or the maximum of a set of random variables. So let's see how we can approach this type of problems. Let's first try to define what is the probability that random variable w is larger than a specific value small w. So this is the probability that the minimum of x1 and x2, this is the definition of w, is larger than any specific value w. For the minimum of two values to be larger than a certain threshold, that necessitate that both values or both random variables are larger than this threshold. So this cannot happen unless both x1 is larger than small w and x2 is larger than small w. This is the only condition such that the minimum of the two of them is larger than w. And since it was mentioned in the problem that x1 and x2 are independent, then this joint probability is the product of the marginal probabilities. So the probability that x1 is larger than w and x2 is larger than w is the product of the probability that x1 is larger than w times the probability that x2 is larger than w. Now we have separated the two random variables and it became straightforward because we know that this is the complementary CDF of x1 and this is the complementary CDF of x2. Recall that the complementary CDF is 1 minus the CDF. The CDF is the probability that a random variable is less than a specific threshold. So the probability that the random variable is larger than a specific threshold is 1 minus the CDF, and this is what we call the complementary CDF. So for exponential random variables, the complementary CDF, if you recall, it was e bar negative lambda 1 w, and this is e bar negative lambda 2 w. So now this is the probability that the new random variable w is larger than a certain threshold. Let's write it here in a simplified form. So it is e power negative lambda 1 plus lambda 2 w. So this is the probabilities that w is larger than threshold small w. Again, this is the complementary CDF of the random variable w. And since it is in this form, e power some constant multiplied by w, so it is the same complementary CDF of an exponential random variable with parameter lambda 1 and lambda 2. So we can, by derivation, either you can first find the CDF, which is 1 minus this value, and then find the derivative of the CDF with respect to the random variable w to get the BDF, or directly, since you know, or you by analogy can deduce that this is the complementary CDF, this is the complementary CDF of exponential random variable, then the BDF of x, the BDF of w, f of w, is equal to the constant, which is here lambda 1 plus lambda 2 e power negative lambda 1 plus lambda 2 times w, and you have to define that w is any positive value, that is w is larger than or equal to 0. So again, this is an example in which we can see that sometimes we might find the probability density function using our understanding of the problem. And this is very common in what we called order statistics, in which we find the probability of a new random variable defined as the minimum of a set of random variables or the maximum of a set of random variables. What we can conclude also here is that the new random variable w is also an exponential random variable. So it is a general rule that if we have order statistics of a set of independent exponential random variables, specifically if we want to find the BDF of the minimum of independent exponential random variables, it will be another exponential random variable whose parameter is equal to the summation of the parameters of the individual exponential random variables. So again, here we have the new random variable minimum of x1 and x2 exponential with a parameter or with average rate of lambda 1 plus lambda 2. Let's try another example. In this example, it says derive the probability density function of the distance of a point from the origin. So what is the distance of a point from the origin? If we have the x coordinate and the y coordinate, then the distance r from the origin is defined as the square root of x squared plus y squared. Then it says, given that its two coordinates, which are x and y, are zero mean, independent, and identically distributed Gaussian random variables. So that means that both x and y are Gaussian random variables. They are independent. So the joint distribution will be the product of the marginal distributions, and they have zero mean, so that is normal distribution with zero mean, and a generic variance or standard deviation sigma. And since both of them are identically distributed, that means that they have the same mean and the same variance. So again, y is Gaussian distributed with zero mean and sigma as the standard deviation. So now we have a new random variable r, the distance from the origin, defined in terms of the two random variables x and y. This is a one-to-one relation, because for every value of x and every value of y, there is only one value of r. However, in order to use the general approach, we need a second random variable. So in this example, it might be convenient to define a new random variable theta such that x is equal to r cosine theta and y equals r sine theta. So as if this is the x coordinate and this is the y coordinate, and this is a point in a space, so its distance from the origin is equal to r, and this is the angle theta, so the x coordinate is r cosine theta and the y coordinate is r sine theta. Now we have two random variables, r and theta, defined in terms of x and y. So if we succeed to find the joint distribution of r and theta, and then we integrate that joint distribution over all the possible values of theta, we get the marginal distribution of R, which is the required. Of course, in order to do that, we need to define both the range of R and theta. Since R is the distance from the origin, so R can be anything larger than 0. And since theta is an angle, so it can be any angle. Theta can be any angle from 0 to 2 pi. So now the question is how to find the joint distribution of R and theta. How to find f of R and theta. So again, this is the joint distribution of x and y. So this will be f of x and y. However, we replace x by a function of R and theta and y by a function of R and theta. And these are the functions that we have here. So it's f of x and y. For x replaced by r cosine theta and y replaced by r sine theta. As we mentioned earlier, both are Gaussian random variables, independent, so the joint distribution is the product of the marginal distribution. So we have for x, it is 1 over square root 2 pi sigma squared, e power negative 1 over 2 sigma squared, x minus the mean squared. So that is x squared. So x squared is r squared cosine squared theta. Similarly multiplied by f of y. So it is also 1 over square root 2 pi sigma squared, e power negative 1 over 2 sigma squared, and now y squared. So y is r sine theta. So that is r squared sine squared theta. Of course, these constants can be multiplied together, so we get only one of them without the square root. And these two exponentials can be written as e power the sum of the exponent, and the sum of the exponent will be negative 1 over 2 sigma squared r squared cosine squared plus sine squared. So that is the second exponential term taken into consideration. And we know that cosine squared theta plus sine squared theta is equal to 1. So we get e power negative r squared over 2 sigma squared. However, the term that we forgot to add is the Jacobian. As we said, we have to, in the case of continuous random variables, we have to multiply by the absolute of the Jacobian, where the Jacobian itself in this case is the determinant of the derivative of x1 and x2 with respect to y1 and y2. In terms of the parameters in this equation, the Jacobian will be the derivative of x1 of x with respect to r. So let's write them. It is the derivative of x with respect to r, and here's the derivative of x with respect to theta, and similarly this will be the derivative of y with respect to r, and this is the derivative of y with respect to theta. By substituting and doing the derivative, that determinant will be equal to r. So we have r also multiplied here, and we have to define that r is larger than or equal to 0, and theta itself is between 0 and 2 pi. In order to get the marginal distribution of r, we have to integrate this joint distribution over the whole range of theta. Luckily here, this joint distribution is not function of theta, so when we integrate with respect to theta, we have the whole expression taken outside the integral, and we are left with integral of 1 d theta for range of theta from 0 to 2 pi, so that will be equal to 2 pi, which cancels out with this 2 pi in the denominator. So we have f of r, the probability density function of r, is equal to r over sigma squared e power negative half r squared over sigma squared. This distribution is one of the popular distributions that are known as the Rayleigh distribution. That is Rayleigh distribution. Our last example for this part of the lecture is as follows. The two components of a signal vector are independent, identically distributed, zero mean Gaussian random variables. Actually, the two components of a signal vector are the same as x and y of any point in space. The standard deviation of the signal components is 5 volts. So that is sigma in the previous example is 5 volts. What is the probability that the magnitude of the signal, what is the magnitude of a signal vector or a vector in space? The magnitude of a vector is r equals to square root of the x coordinate square plus y squared. And since the coordinates are zero mean Gaussian random variables, similar to the previous problem, we can say that r will be Rayleigh distributed, and it was function of, or it was dependent on the parameter sigma, which is given as 5 volts here. So from the previous problem, fr of the Rayleigh random variable is equal to r over sigma squared, which is 5 squared in this case, e power negative 1 over 2 r over sigma all squared for r larger than or equal to 0. And if we are asked about the probability that the magnitude does not exceed 5 volts, so this is the probability that r does not exceed, so it is less than or equal 5. So it can be obtained by integrating this probability density function from the lowest value, which is 0 for this random variable, to the threshold, which is 5. So as if we are getting or obtaining the cumulative distribution function, and this PDF is easily integrable, and you can find that the CDF at any value r is equal to 1 minus e power negative half r over sigma all squared. And by substituting for small r by 5, you can easily get the required probability, which will be in this case 1 minus e power negative half r equal 5, and sigma is also equal 5, so it is just 1 minus e power negative half. Now we will use another approach other than the inverse transformation approach, and that is the moment generating function approach. Previously, we knew how to calculate the moment generating function of any random variable, and we mentioned a theorem that is called the Uniqueness Theorem. Let's mention it again here. It says that if x and y are two random variables with moment generating functions mx of t and my of t, then if both moment generating functions are exactly the same, then both random variables will have the same probability distribution. So simply the Uniqueness Theorem says that for any random variable with known probability density function, there is only one expression for the moment generating function. And inversely, for an expression of the moment generating function that uniquely defines the probability distribution of a random variable. So, for example, if you know that the moment generating function of the binomial distribution mx of t is given as p e power t plus q power n, and then you have another random variable y for example, whose moment generating function is as follows: 0.2 e power t plus 0.8 power 5. So this expression is the expression of the moment generating function of a binomial random variable. So since you are given this moment generating function, you can with confidence tell that the random variable y is binomial distributed with parameters n equals to 5 and b equals to 0.2. Of course, q is equal to 1 minus p, which is 0.8 here. So you can say that the BDF fy for small y is equal to 5cy 0.2 power y times 0.8 power 5 minus y. So this is the strength of the uniqueness theorem, which relates which specifies that given a moment generating function, you can uniquely identify the probability distribution. So how can this uniqueness theorem be used in order to find the probability density function of a random variable defined in terms of a new random variable? Let's use this theorem in a set of examples as follows. Let's first find the moment generating function of random variable defined as a non-random variable x plus a constant a. So if we know random variable x and we know that its moment generating function is mx of t, recall that the moment generating function was expected value of e power x t. Now if you have random variable y defined as x plus a, let's find the moment generating function of y, my of t. So that is what can be written as m of x plus a of t. So this is the expected value of e power y t. This is equal to expected value of e power y is defined as x plus a t. That is equal to expected value of e power xt times e power at. Since both e and t are not random, they are parameters, so they can be taken outside the expectation. So that is e power at times the expected value of e power xt. So that is e power at, and this is the definition of the moment generating function of x. So for a new random variable y defined as random variable x plus a, its moment generating function equals to the moment generating function of x multiplied by a constant e power at. And then once we calculate the moment generating function of x, if the resulting expression is one of the known expressions of the moment generating function, then we can get the probability density function of y. Another case, when we have random variable y defined as a scalar multiplied by random variable x. In this case, we can find that the moment generating function of y, as defined by the expected value of y t, is equal to the expected value of e power ax t. If we just rearrange the symbols, so that is the expected value of e power x at, and this is the definition of the moment generating function of x with parameters at. So again, we can obtain the moment generating function of a new random variable in terms of a random variable x for which y is defined as a scalar value of x. Let's solve this example. In this example, we have a random variable y for which we want to find the moment generating function, in which y is equal to x1 plus x2, and the x1 and x2 are both independent random variables. So again, this is a generic problem where we are not specifying probability distributions of x1 and x2. Instead, we want to find the moment generating function of x1 plus x2. So that is the expected value of e power yt is equal to the expected value of e power x1 plus x2 t. So that is the expected value of e power x1 t times e power x2 t. Since x1 and x2 are independent random variables, you recall when we derived the expected value of x times y for the case when x and y were independent, that was equal to the expected value of x times the expected value of y. So similarly here, this is equal to the expected value of e power x1 t times the expected value of e power x2 t. Make sure that this step is not correct unless x1 and x2 are independent. Of course, this is the moment generating function of x1 times the moment generating function of x2. So we can conclude here that for any two independent random variables added together, the moment generating function is the product of their moment generating functions. And this can be generalized for any number of random variables added together. The moment generating function of the addition of n random variables is equal to the product of the moment generating functions of those m random variables. If we apply this approach to the first problem that we solved, in the first problem we had x1 and x2 Poisson random variables independent, and x1 had a parameter lambda 1 and the other random variable had parameter x2. So if we obtain the moment generating function of the Poisson random variable, it is e power lambda e power t minus 1. So for x1 that will be e power lambda 1 e power t minus 1. For the other random variable x2 it will be e power lambda 2 e power t minus 1. And since they are independent and we were seeking the probability density function of their addition, so the moment generating function of their addition is the product of their moment generating functions. So this can be rewritten as e power lambda 1 plus lambda 2 times e power t minus 1. And again, this is the same form of the moment generating function of Poisson random variable with parameters lambda 1 and lambda 2. Then with the uniqueness theorem, we can say that y is a Poisson random variable with parameters lambda 1 and lambda 2. Of course, this is the same result that we reached using the inverse transformation approach, but using the moment generating function approach, it is much faster. However, be cautious that the moment generating function approach does not necessarily help us find the PDF. It is useful only when we obtain or when we get the moment generating function in one of the forms that we already know before, such as in this example where x1 and x2 were Poisson random variables. Finally, if we want to combine the two conclusions that we obtained before, if we have a random variable defined as a scaled version of random variable, or we have new random variable defined as two random variables added together, so that is if we have one y defined as ax1 plus bx2, then the moment generating function of y will be equal to the expected value of e power yt, so that is e power ax1t times e power ax2t. And if the two random variables x1 and x2 are independent, then we can write this is the moment generating function of x1 with parameter at multiply by the moment generating function of x2 multiply by parameter, of course this was b, parameter bt. So this is the strength of the moment generating function approach, and this strength is more beneficial when we deal with independent random variables. In summary, we studied two approaches to find the probability distributions of new random variables defined in terms of non-random variables. Those approaches are the inverse transformation approach and the moment generating function approach.